which is an enormous waste of fresh water. And they came to us and said, can you grow algae on this? Can you utilise this nitrate waste? And also, could we use the biomass for anything once we've done it? So, just to give you a bit of background, so the groundwater contains very high concentrations of nitrate. Because of where we're situated, there's an awful lot of farming, and we get a lot of fertiliser runoff into rivers and also down into the groundwater. So what they do is they use resin-filled columns. It's an ion exchange system. So the nitrate ions are replaced by chloride ions, and it passes through the resin. Now, they have to rejuvenate these resins, otherwise it becomes something else that they have to deal with as waste, but also becomes very costly. So they wash it by putting very high saline water through it. What they end up with is this waste of nitrate and brine. So they provided us with 10 litres of this crude brine wash, but they also provided us with a diluted brine as well. And this just gives you an idea of actually what's in there and what are our UK drinking water standards. And as you can see, unless it's highly diluted, they really can't pump anything back into the system. And you can see from the chloride and sodium, it really is very highly saline. So we did some very small-scale laboratory experiments using a range of both marine and freshwater species. And what we did was we took the standard medias that you would use for these particular species, and as a control we had the media plus its usual nitrate source, its NO3 source. And then for the experimental solutions, we used the same media, but we replaced the NO3 with a proportion of this brine waste, which was equivalent to the same concentration as the media. And what we found was, yes, most of the species do actually replicate quite well. But this is just a little visual for you to see that they do actually grow quite well in the diluted brine waste. So then we went on, we looked at some brine tolerance. Now these are laboratory experiments using 50 ml flasks of culture. And what they were subjected to were the control, the normal standard media, and varying proportions of brine waste, so varying concentrations of nitrate included in the brine. And of course, as you increase the concentration of nitrate, you also increase the concentration, the salinity of them. So here we have 3 marine species, but we also thought we'd test a freshwater species as well and see if we could acclimate that to a higher salinity. Now, as you can see in all of them, quite nervous, can you tell? I'm shaking, don't I? The standard media, which is in black on all of these, our brine waste with the equivalent nitrate performs as well, if not better, in every case. And in fact, the higher brine or nitrate concentrations also perform very well. So they seem quite tolerant not only of the high nitrate, but also the higher salinities as well. Even the chlorella, you can get it to tolerate the high brine. I think it will be no surprise that none of them grew in 100% pure brine. The cells just rise as we would expect. So then we went on. We have a small area at the Botanic Gardens in a polytunnel. Now these are what we call the socks. These are 5-litre plastic bags, bespoke, made by me. This is day 1, this would be day 3, and this is day 5. So we're growing quite quickly. And again, what we've done here, well actually from the laboratory experiments, as we found that they could grow very well on this brine waste, we used the standard media for our marine species, minus the NO3, but with the equivalent in brine waste. And for these experiments, we bubbled them with either air or air plus a 5% CO2 mix, because we thought we'd just have a look to see what that effect So for what I'm using here is optical density as a proxy for biomass. And what I'm presenting here is a winter versus summer growth on them. Now, I think it'll be no surprise to anybody in this room to see that summer growth is far greater than winter growth. The optical densities for Tetracermus are 6 to 7-fold higher. And this is borne out also in the dry weights that we get, which are at least twice as much, if not 3 or 4 times higher, that you get from a summer growth than a winter growth. You can see that actually when we stopped the experiment here, which unfortunately I had to stop, it had started to have some issues with it, they were actually still growing. They were still going up. We hadn't actually got stationary phase and anything. So just to show you what happens in the winter, although we had quite a long lag phase in winter, actually the optical densities never reach a high point like the summer ones would. And they just level out, even if you look at your nitrate. So in winter you're never going to get as big growth. So we then moved on, so we scaled up again to some PBRs. These are skilled reactors. And so far we've used 1 marine species and 1 freshwater species. So in one of our reactors we put the standard F2 media with the standard NO3, and in the other reactor again we've replaced that with the nitrate brine waste. And we've used Phaeodactylum tricornium, that seems to be the one that grows the best, and Calabrus, our freshwater species. And we've done these in 100-litre capacities. So from the Phaeodactylum, this is winter again, and as you see, quite a long lag phase, but the brine experiment performs as well, again, even in the scale-up, as the standard F2 media. So Phaeodactylum so far is the one that we have laboratory, SOX and PBR, so we've got the whole scale up on those. So under controlled conditions, at a 12-12 light cycle, 24 degrees in the laboratory, for the optical densities we can see not too far away in summer from our scale up onto our SOC experiments at 5 litres. I am currently running the summer Phaeodactylum and the PBR to see what we get from that as well. You do lose some biomass as you scale up, but it seems not to be a huge amount at the moment. For the winter, so this is our winter PBR, again at day 15. The comparison, we actually got slightly more in the PBR than we did in the SOC. But again, it's not a significant difference. So winter to summer, the scale-ups seem to be quite comparable. So what next for our experiments? So we do need to conduct a few small experiments to properly look at the nitrate utilisation, to look at the nitrate drawdown. Some initial experiments indicated that some species were more efficient at taking up the nitrogen than others, so we need to identify those and to actually look at those efficiencies. As we've upped the amount of, as we've increased the amount of nitrate and therefore the amount of brine waste that we're using, it would be interesting to see what their efficiencies are, because there's no point in throwing a lot of nitrate at them if they're not using it, because you still end up with some waste in that case. We do have some, I've got some algal pellets stored for some metabolite analysis, so we will be looking at lipid composition on the various concentrations of brine waste, carbohydrates, proteins, that sort of thing. And those are some analysis that we still need to run. I've been given the data for the chlorella quite recently, so I need to look at and see what the efficiencies of the PBR for the chlorella are on scale up from the laboratory experiments. And as I say, I'm currently repeating the Phaeodactylum experiment in the PBR in warmer conditions. So I've basically showed you optical density because it gives you a nice visual of what the biomass is doing. But as you can see, we have measured, or we have taken samples for a variety of what's the word I'm looking for? Parameters. Thank you. So we do have quite a large data set to look at, or I have quite a large data set to look at for each of these experiments that we've done. So on to our future experiments. We have a very nice set of polar diatoms to look at. The idea will be to start in the laboratory, looking at temperature tolerances. I think it's fair to say they are not going to get the same sorts of conditions that they would get in their own environments. Most of these will survive quite happily at 2 and 4 degrees. So that's what they're used to. So the idea is just to bring them up a little bit to 5 and 10 degrees, because that's probably more realistic of an average in a British winter daytime temperatures, but obviously that will go down at night. And what we're going to do is we're going to compare their growth and the metabolites of those with some of our temperate species. Now we have some of this, the winter data for our temperate species. It'll be an interesting comparison to see if we can get a greater biomass from them. These ones are likely not to be grown on a biomass at the moment. That's not the idea for them. We're just trying to do this temperature thing to see. And the idea is, can you change from a temperate species in the summer, and then you just keep rolling on? You don't lose any of your productivity if you can roll on into winter and use species that are more cold tolerant. So you can keep your productivity of your biomass fairly constant. So we'll start these in the laboratory and then scale up to some new 10-litre standalone PBRs that would hopefully have been delivered this week, I'm hoping. So these are our future innovations. This here is our new PBR setup. They are purpose-built. I will be running some experiments in them, in the 2 that are being delivered, just as a look and see if they're working, see if we can improve them. The idea is that they will aerate from the bottom. There are various outlets for either introducing gases or sampling from a relatively closed system. And again, as Sean was saying earlier, there is a new glasshouse coming online. Things are speeding up. I can't give too much information at the moment. I don't have too much information on it at the moment, but it's started to move quite quickly. The glasshouse is going to be put next to this building here at the Botanic Gardens. Funding has been secured for it already, and the idea is to make it a fully functional GM compliant facility. So finally onto our outputs. Obviously we will be uploading our data onto the NLP website. Yes, hooray! Still a bit to do. I've still got quite a lot to look at. But yeah, I've really just given you a very brief snapshot of what we've got here. And obviously the paper writing and reports. As you can see, we've applied for, or we have been awarded a substantial amount of funding recently as well. So we will be looking into some anaerobic digestion. This for our polar species as well, so as well as looking at productivity of them. We'll be investigating ice-binding proteins in polar species and how, if it's possible, to manipulate using nutrients production of these ice-binding proteins. And again, another line from the AD net, we've secured 60k for. And the idea of this is actually to give people some really decent empirical data on anaerobic digestion processes. So these are my colleagues up here, and I'm sure many of you have met many of these people. Thank you very much for your time.
Thank you, Louisa. Any questions from the audience?
When you do the addition of the brine water, what was the increase in salinity? Because the nitrate is a major product in brine
for even at the 5 times the nitrate concentration, that was really only up to 5 to 10 points salinity that it went quite. And actually chlorella, even though it's a freshwater species, will survive quite happily for a short period of time in quite saline waters, as I found my costs when we were running some marine species in our first stocks, and they got completely infested with chlorella. It's been a weed. So actually, yes, the salinity doesn't go up that much, but the marine species will keep suitably doing. Unfortunately, situated in Cambridge, we have to make up with nutritious seawater, but if you could use a seawater source, then
Do you think these algae grown on wastewater can be used for food applications?
this is something we need to look into. And this is why we have some of these pellets to look into the heavy metal added as well. Each batch of brine that is produced is slightly different in its composition. And so you will get variability not only in the macronutrients but also in trace metals and heavy metals if they are in there at all. We also have to consider possible viruses and bacteria as well. So you would have to screen for things like E. coli, etc. Certainly the brine waste that has been coming through that we've used for our experiments, we've autoclaved first to remove any bugs. That doesn't affect the nitrate concentration. We measure the nitrate in it after as well, and that doesn't affect the nitrate concentration, and we add trace elements as you would into a normal media. But that's certainly something we would need to look into before we could say that it could be certainly used, certainly for human use, or even as animal feeds, because it is essentially wastewater. And that's the thing, it's finding out what the end product could be for something like this, whether this could scale up to a very large scale for bioremediation for the nitrate denitrification, but we will end up possibly with waste product.
I have also a question regarding the phaeodactylum in the PBR. So in the brine, did you only did it for batch, so for 40, 45 days, or did you try to do it as a continuous culture?
So the phaeodactylum in the winter, that was a batch culture. So we're just doing batch cultures at the moment. It's been more time than anything else rather than continuous or semi-continuous cultures. I will be trying to replicate the same this summer so that we have a consistent data set. But yeah, I see no reason why they couldn't be run at least semi-continuously. Phaeodactylum seems very obedient as far as these sorts of experiments are concerned.
Thank you. No more questions? No. So moving on to our last speaker for this afternoon session. It's Franziska Kugler. She's from KIT in Germany, and she will talk about life cycle analysis of microalgae culture in a recirculating aquaculture system for bioremediation.
I think everybody can hear me now? I hope so. Okay. So thank you very much. First of all, I'd like to say that I'm not an algae producer, as we heard presentations of all the algae, the pilot partners in the afternoon. So Anneliese Ernst from who's a pilot operator from Saarbrücken, was asked to give a presentation, but unfortunately she cannot be here. So I'm representing the pilot of Germany, and I'm responsible within my research group for the LCA, for the life cycle assessments and sustainability analysis. So that's why today I'm going to present the LCA of the microalgae culture in a recirculating aquaculture system, which is the pilot of Anneliese Ernst for bioremediation. So first of all, explained my methods, what is the LCA approach and how we collect the data, how we set boundaries for our systems and which assumptions we have. And then I will show you some results of the LCA. Then we can discuss the results and I give you some an outlook. So as a background, it's supposed to be a research relating aquaculture system, which means that the algae is produced to be fed for the fish, feed for fish, or fish larvae, and then the wastewater should be treated by the algae again. So there should be a closed loop, but unfortunately it is not yet. So the algae is not integrated into the system at the moment, so it's a standalone algae production at the moment. So they also don't have any downstream processing, so they stop at harvesting. That's why we modeled the system according to energy application, as it's the goal of our project. So this is the system, some graph. So we have an inoculum production, which is in a flat panel PBR. Then the cultivation should be in a tubular reactor, which is 100 liter. It's very, very small scale. And then we have a harvesting, which we just modeled as microfiltration to get dry algae. And then we produce biogas. So this system also sets our boundaries at the same time. So we model mainly energy and materials that go in the system. And as output, we have 1 megajoule of biogas from algae. Okay, so for our LCA modeling, we used data from the pilots, which we collected via a Excel-based questionnaire. It's a data requirement sheet. It's actually very simple to fill in, but some data is missing, or the operators just cannot deliver these data. We also had some visits of the pilot and interviews to gather the data. Where data was not available, we used assumptions, and these assumptions are mainly based on own calculations, and a former colleague of me made a model on algae production, and this is where my assumptions for the LCA model are based on mainly. So we have data from the pilot of Anneliese for the inoculum production, so for the 5 liter flat panel reactor, and for the cultivation in the 100 liter tubular reactor. But we had to make assumptions for the downstream processing, as I already said. So we had to make assumptions for harvesting. So we used microfiltration, and for biogas production. Okay, we used an environmental life cycle assessment, and therefore we have a special software. It's called Umberto. It's not very common, but we used it. It's a German software, so we're from Germany. We use it. And we have a database for background information to have the pre-chains, which can be integrated in the system. It's called Equivalent. And as impact assessment method, we use the recipe. This is a very common impact assessment method. So you just don't need to read the the things. It's just like, can I just, there's a laser pointer. Okay. So this is the inoculum production. So you just have a look at the rectangular signs here. This is the inoculum production in the flat panel. This is in the tubular reactor. This is the microfiltration. This is the biogas production, and this is in the end the output biogas. So as called Sankey diagram, and you see the arrow, the thickness of the arrow contributes to the amount of flow. So this is energy used mainly, and the whole system is regarding now global warming potential, which is mainly driven by the energy that is consumed during cultivation. So you see, it's mainly the energy used during cultivation which comes in here and just passes through the whole process chain. It's just a snapshot again. So just to see that the main contributor is just from the energy production, energy consumption up here, which goes to the cultivation. So in the end, you have the product is 1 megajoule of biogas. Okay, so because these results look really bad, we tried to just compare it to the economic model of Louiza and try to see which amounts of energy consumption he uses. So the values above is from the economic model for air sparging, circulation and heating. Louiza doesn't include the inoculation, but just the cultivation period, so in the future reactor land. So here we have air gassing and pumping, and you can see the differences in the amounts. So we tried to adapt the model and just said, okay, if we could reduce to these to 1/15 of electricity consumption, how does it look like then? So again, you don't have to read it. Here again is inoculum production, cultivation, microfiltration, and biogas production. What you can see is that the flow from here up is much smaller, but nevertheless, the flow from inoculum production now is getting bigger again. So, but this is not. This was not displayed in Louiza's model, so that's why it stays like this, and the whole contribution comes from the inoculation part now. Okay, so the results, don't be shocked, the results are really bad. So this is the deviation from natural gas production, and this is orders of magnitude difference. So you see the biogas from algae compared to natural gas, it's the gray bars, and here you can see the impact categories. We also compared to, it's like that. Okay, so then we have the 1/15 of energy consumption as Louiza used, so we see it's slightly better, the green bar here, but anyway, still horrible. If we just compare to another biogas from the database, from conventional biogas, you see that this is much better, and in some cases even better than natural gas. So the most common impact categories are, for example, climate change, which is here. And here we are 6 times higher in IG projection than it is for natural gas. Okay, so to discuss it, I mean the values, as you can see, it's just coming from energy consumption. So the main goal is to reduce this energy. I have to say that in this specific pilot, they use, for example, 2 devices. It's a pump and a compressor during cultivation, which runs 24 hours a day and 300 days per year. So you could maybe reduce it during night. You don't need to pump the culture and don't need to sparge it. And there you could reduce and find there's potential to reduce. And so, like the LCAs shows that it's just energy, and that energy impact is that big. You just don't see other impacts from, for example, fertilizer input or something like that. It's just hidden by the energy. So the energy savings are crucial to go at least towards a positive life cycle result. Or the other option is to increase yield in the end if you just balance it. Okay, so to sum up, what we're trying to do is in future is maybe to look at other applications of the biomass, the algae biomass, for example, for fish feed, which was the actual goal. And also to optimize, so for example, to reduce the energy consumption. And maybe we also try to upscale, which can be some economies of scale effects, and but therefore we have to make reasonable assumptions, which we still don't know and still are in discussion. So that's it. Thanks a lot.
Francesca, are there's also good news, in fact, to conclude questions? Yes, Alla?
Thank you. Yeah, really interesting talk. Thank you very much. But just for comments, I think so. Biogas production is not. We need to use algal biomass for something more useful than biogas production, and it's good that then it's visible from economical evaluation by LCA. It's done basically. Thank you. And how is LCA take in account, for example, like fish feed or some other application? Can it be developed in other tool? I mean, in other final
You
application?
can also make an LCA of fish feed, and you can have, for example, you can have both, like the recirculating aquaculture system suggests to have fish feed, and from the surplus biomass, you can produce energy. So you can have many products in the end, and you can make kind of biorefinery, geology, and then make an LCA of all, and to sum it up in the end, which makes it much better then.
Good. And another question. So, if final composition of the biomass, if it's high on lipids, for instance, it will increase biogas production.
Lipids won't increase biogas production.
Okay. Thank you.
But lipids make it more. For lipids, it's more reasonable to produce biodiesel.
What is can be another solution?
Okay, there's another question.
It's related to the method. Did you include infrastructure in your assessment?
Yeah, it's included.
It's included. Because I don't remember by heart the figures, but some of the figures are not directly related to the energy consumption, as far as I understand. The comparison of the results, the bars.
The bars, okay?
Yeah. Because you wouldn't say that all the categories you have in the results are marine electrification and all those things are related to the energy consumption.
No, but most. It's also for the biogas plant production and things like that. This is the pre-chain.
Do you count also the biogas production as such? So for the methane emissions from the biogas production, the digestive and all those things. It's not only the.
No.
I think it's quite strange that you actually try to end up with biogas starting from a PBR, a photobioreactor. I think nobody intends to do. So normally if you have a photobioreactor, they focus on one species, and then they focus on a high-end value product. And for example, like our reactor at Alpro, okay, we might tend to go for an option like biogas, even not that is the best option, we know that. But then you should compare, I think, for example, with references like sludge treatment or something, not with actually starting from a photobioreactor principle towards biogas. Then, of course, you end up, and especially when you compare with natural gas, because you didn't include any waste treatment benefits or something, so it's quite, well, to me, it's quite a strange comparison.
Yeah, we just went for the biogas because we thought the goal to have an energy product in the end. Probably makes sense to go for another product for sure, but it just selected this.
I think it would be more easy if afterwards to need is to compare with fish feed, for example, to take the oil as reference. You will have not kind of 1 megajoule of biogas, but 1 megajoule of the calorific value of the oil you have in the algae. Not as such from the biodiesel, because then you have other assumptions. But then it makes maybe more easy for assumption afterwards to